Okay, so it's been a week and I feel so much better. I just needed a ton of sleep. But I'm feeling really good and raring to go. So let's get into lesson 6.5. This is the derivatives of derivatives. Okay, so yes, you can take the derivative of a derivative, which means it's like the original is the original graph. The derivative is like a bunch of slopes. And so you're taking the slopes of the slopes. Okay, I'll show you like later on graphically what I mean. So algebraically, this is what I mean. Here is our original function. All right, now what I want to do is I want to find the derivative. So this one is asking me to find the derivative. That's what dy over dx means. Find the derivative of y with respect to x. And we can just do that because this is a nice polynomial row. So why don't we just do the derivative of each of the terms? And we'll do that by applying the power rule. So 2 times 4 is going to give us 8. X to the power of 1 less than the 2, which is just 1. I'm not going to write the 1 though. This term has a 1 in the variable for the exponent. And so I'm going to take that 1, multiply the 7. So I'm going to get -7. But minus 1 for the exponent will make a 0. So x to the power of 0 is 1. That means I don't even want to write that. The 3 itself, when you take the derivative, is going to give you a 0 because it's a constant. So I'm not going to write that either. That means I'm done my derivative in purple. Noticing that the next question is asking me, well, here is the form for a derivative, but what are they asking me for? So by putting that other part on the outside, they're asking me, I want the derivative of my derivative. That's what this is saying. Okay, so they want the derivative of this guy, not the original function. But that's okay. I mean, it's an even easier function right now. This has a power of 1, so let's just apply the power rule. 1 times 8 is going to give us 8. Okay, then you're going to subtract 1 from the exponent, which means x to the power of 0, and that means my x disappears. Okay, taking the derivative of the -7, you're just going to get a 0. So my second derivative is just 8. What you guys just found, well, what I found and you guys watched me find, is your original function was something like this. Your derivative, y prime, was the purple 8x minus 7. And then the second derivative, which I'm going to write as y double prime, that's how we say it, y double prime, is going to be 8. So yeah, I could keep going and find a triple prime, quadruple prime, and so on. So you have first derivatives, second derivatives, third derivatives. You can keep going. I think I've also actually seen this written as d2y over dx squared. So if you see that sort of notation, also know that they're looking for y double prime or the second derivative. Okay, now let's take a look at the second question. Second question is a little bit tricky. What they're saying is you have your original function. Okay, so this guy right here. The only problem is I really want you to understand what happens when I change up the bottoms. They're asking, like both of them are actually asking for the derivative, but they're saying it with respect to different things. So this is saying with respect to a, and this is actually saying with respect to x. When I say with respect to a letter, they mean that that letter treated as a variable, and any other variables you see in the question, pretend that those are regular numbers. So what I'm going to do is I'm actually going to do the second one first because I think you're used to dy over dx more. And let me show you what that looks like. Okay, so again, with respect to x means that everywhere I see an x, that is my variable of interest. Any other variables like the a and the t, pretend that those are numbers. Just pretend that those are like part of the coefficient. So let's take the derivative. 3 times 4 is 12, x to the power of 2, because I subtracted 1 from the 3. All right, this x has a 1 as the exponent. We're going to take that and multiply the entire coefficient. So we're pretending that that a is part of the coefficient. It's just a regular number. So plus 2a. And then we're going to subtract 1 from the exponent. So that x disappears. Now that last part, that t, is again, we're going to pretend that that's a number. Take the 2, multiply the t. So negative 2t is my coefficient. And then the x, you're going to subtract 1 from the exponent. And again, don't write that 1. Okay, so this is what it would look like if you treated the x as the variable. I'm going to do this a little bit differently now for a. What we're going to do now is only the a is going to be the variable that we are interested in. Every other variable in there, like the x's and the t's, pretend that those are numbers. And so this entire thing is a ginormous number. Just pretend that that's a huge number. If I take a derivative of that, I'm going to get a 0 because the derivative of a whole number, like a constant, is 0. Plus. Now this guy, I want to rewrite this as 2x and then the a because I'm going to treat these two as numbers and my a is going to be the one with the exponent because I'm treating that one as a variable. So 1 times the 2x is going to give me 2x, but the a is going to lose an exponent, and so that's a to the power of 0, and it disappears. This last one, again, because I'm doing it with respect to a, t and x are going to be treated as numbers. And so when I take the derivative of a number, I'm going to get 0 again. Okay, so I get 2x as my final answer. Notice that the green answer and the purple answer are different. And so whatever you treat as your quote-unquote with respect to, that's going to give you a different answer, even though the original function is the same. So there are a couple different ways that we can write this, and I've already shown you some of them already. I know that I just said already twice, but that's okay. Y is our original function. Y prime is the first derivative. Y double prime is the second derivative, so the derivative of the derivative. Y triple prime is the derivative of the derivative of the derivative. You get it. Quadruple prime and so on. Like this could keep going. You can also write it as f at x. So if you use the f, you know f prime at x. Second one is f double prime at x. F triple prime at x. F quadruple prime at x, and so on. Okay, the other two, I actually haven't seen this one very much, but my coworker wrote it down in her notes, so I'm assuming that maybe she has. But usually I see these 3. Okay, so just know if you were to see any of those in the middle, then you would know I need to find, the double or triple prime. Okay. I also want you to notice that every time you go from, actually, you know what? I will share that with you later on when I have an example. I will share that with you right here. So they're asking for a 5th prime, like 5, like many derivatives. Okay, so what we're going to do is here is our original function. We're going to do the first derivative, and you'll see that it actually gets a lot easier as you go. We're going to take the 3, multiply the 1 over 18, and so I get this guy right here. And subtract 1 from the exponent, so x squared. Take this guy, 2 times 1 over 12, and I get 2 over 12. Subtract 1 from the exponent, x to the power of 1. Okay, this has a 1 right here, multiply the 1 over 6, and so I get 1 over 6 again. But subtracting 1 from the exponent gives an x to the power of 0. That disappears. And then the negative 3 over 4, when you take the derivative, it's going to give you a 0. Now I can clean up this function on the side right here. Actually, I have no idea why I didn't get out of here, because you're supposed to be a 1 over 6 as well. I see lots of 6s, 666. Okay, maybe my lesson is a little bit evil. All right, now going into the second derivative. Second derivative, we're just going to do the derivative of the derivative. So we're going to do the exact same steps, but we're going to use the derivative function. So 2 times 3 over 18 is going to give you 6 over 18. Okay, take 1 away from the exponent. It's going to give you a 1. right? But don't write the 1. Okay, so get out of here. Then you're going to take this one, multiply the 2 over 12, and so you get 2 over 12, which I've reduced to 1 over 6. Subtract 1 is x to the power of 0. That disappears. And then the 1 over 6 at the end is a constant, and so that becomes a 0 when we take the derivative. So this guy, all nice and cleaned up, gives you this right here. Okay, now if I were to continue to do the derivative, sorry, this was 1, and then we multiply. So I'm going to get 6 over 18, but when I subtract 1, I'm going to have my x disappear, the 1 over 6 beside it disappears, and I just am left with a constant. Now when I want to take the derivative of the constant, you're just going to get 0. And then try to take a derivative again, you're just going to get 0. So what I do want you to notice is it looks like the original function was a cube, right? Some sort of cubic graph. Then notice that the next one is a squared, and the next one is a linear, and then the next one is a linear. This is a linear, and that's also a linear. So we go down in steps in terms of degree every time we take a derivative, but at some point it's always going to be linear because we don't really have anything past a linear. Okay, so let's try some more examples. Example number 4. Determine d2y over dx squared, so basically the second derivative, of this original function. Okay, so that looks like a product rule because there's two things multiplying each other. In fact, I think maybe I'm going to shorten this to just that, and then this. Okay, so let's take the derivative first. This is the first derivative. And I hope you guys remember the product rule. Product rule is where we keep the first function, take the derivative of the second. Okay, so let's see, that would be 4x, right, minus 5. Okay, then we're going to add our derivative, no, actually, it's the second function, 2x squared minus 5x plus 4. So we don't touch that one, but we're going to take the derivative of the blue. 6x plus 6. I'm sorry if that's a little bit fast, but I'm assuming that you guys already know the power rule. Okay, so this is our derivative, our first derivative, and if I really want to, I can just erase this just to match the notation that they actually have. dy over dx. Okay, now they want d2y over dx squared. So that means you have to take the derivative again. So d squared y over dx squared is equal to, okay, how do you take the derivative of this? Well, I mean, it is pretty much the same thing again. So what you have here are two product rules. So you're just going to have to do the product rule twice. Let's do the very first blue and green. Keep the first one. Okay, multiplied by the derivative of the second. So the derivative of this guy is going to be 4. All right, plus, we're going to do the same green. Don't touch it. But the derivative of the blue now. So 6x plus 6. All right. Now that guy right here is the derivative of these two. Then we're going to add, okay, so there's my add, right? The derivative of the second green and blue using the product rule. So I'm going to write that maybe right here. Okay, so that's going to be this one. Let's keep the green. 2x squared minus 5x plus 4. Derivative of the blue, which is 6. Plus derivative of the blue. No, not the derivative of the blue, sorry. Keep the blue. And derivative of the green. Okay, so that would be our derivative of our derivative, and I would actually just leave it like that. I wouldn't simplify anything unless, they told you so, but it looks like they said, don't simplify any further because I really want to see all of your steps clearly, and when you start like multiplying and smushing things together and simplifying, it gets too complicated. So we'll just leave it at that. So what happens if you see a word problem? All right, so here's a word problem, and I want you to understand what the derivative or the second derivative actually means. In this case, we're talking about the population of a bacteria culture over T hours. Okay, so we have our original function, and N stands for how many number of bacteria you're talking about, and T obviously stands for time. Now, when you find the growth rate, so again, I'm going to use my purple. The growth rate means give me the derivative because the derivative, again, is a slope and rate is a slope. So you're trying to find the growth of the bacteria over a certain amount of time. And you can find the derivative of this guy. 3 times 12 is going to be my 36, and then t squared, right, because you're going to subtract 1. This is a t to the power of 1, multiply. So I'm going to get 200 without the t, because again, you're going to subtract 1 for the exponent. But what does this actually mean? Like, what does this function actually show you? This is a rate of change. A rate of change from the number of bacteria, okay, per hour. That's what this rate of change is. A rate of change is just a slope. And so if you decided to say, I want to know what the growth rate is after 5 hours, you would put 5 into the t, and whatever you guys got from your answer, that would be that number of bacteria after, like, per hour, after 5 hours. That is what the growth rate is at 5 hours. Okay, so the number of bacteria per hour at the 5th hour mark. So then what does a double derivative mean? Like, what does a second derivative mean? And again, you know how to take the second derivative. I'm not going to go over how I got the 72t because you can see it from the original purple function. But this guy right here, what it means is you're still trying to find a rate of change. Except your rate of change is of your growth rate. Okay, so you have the number of bacteria per hour. That was n prime. Since you want n double prime, you're kind of comparing this over hours again. You're doing the rate of change of the growth rate. So how much is the growth rate changing with respect to time? So what does n, like for C, what does n double prime actually represent? It means the rate of change of the growth rate itself. So what is the change of the first derivative? All right, so let's take a look at some graphs now. Okay, so our very last question, example number 6, gives us an original function, and that's going to be in blue. So this guy is g at x, okay, and we have something like x cubed minus 2x squared minus 4x plus 3. I kind of graphed it already. Now, what I gave you are the x-intercepts in red. You can do that using, what was it? I think it's advanced functions knowledge, where you do factoring, right? Like with the factor theorem and so on, or polynomial long division. That guy's so much fun. But basically, I gave you the 3 x-intercepts, 1, 2, and 3. Okay, now we know it's an x cubed. It is a positive x cubed, and so that's how I got the general shape. But I could always find, the peaks as well, and that just gives me a little bit more information, because what they're going to ask me to do next is they want me to now graph this guy, which is g prime at x. So, I mean, I could always do the derivative. The derivative is just going to be algebraically 3x squared minus 4x minus 4. So notice that you have some sort of a quadratic, but what I really want you guys to understand is how the shape actually works. So I'm going to keep the same scale. Wherever you see that the original function had a slope of 0, which are usually the peaks, right? So it looks like it's at an x value of 2 and somewhere around here, maybe negative 0.61. So I'm going to mark those places right here and here again. Since this is x and this is now g prime at x, or in other words, my slope graph, since the slope is 0 at these x values, I'm going to put it as a 0 height on my slope graph. Okay? Now let's take a look at the slopes all along the function. What color do I want to do this in? I'm going to do this in maybe pink to show positives and negatives. Okay, so let's use pink. Okay, so here is a positive slope, less positive, less positive, less positive, all the way to 0. So in the positive regions of my slope, it's becoming less and less positive all the way to 0. All right? This side as well is going to become positive, more positive, more positive, even more positive. And so from a 0, it's going to become more positive, more positive, more positive, and you're going to get something like this. So notice that it's starting to shape up as the x squared graph. Now using a nice blue. Okay, so in the middle, you have 0, negative, more negative, very negative. 0, more negative, more negative. Then it's going to become less negative, even more less negative, and all of a sudden 0. Less negative, 0. There you go. You have your quadratic. And there is a special point. The point of inflection, which is somewhere around here, will actually become this guy right here. Okay, so it's going to become your vertex of your quadratic. And if we do a double prime, g double prime x, we can do that algebraically. So taking the derivative of my first derivative, that's 6x minus 4, you're going to see some sort of a line. And that makes sense because it's 1 degree less. Wherever you see a slope of 0 in the middle graph, that's now going to be my intercept of my g double prime, because this is now the slope of the slope graph. Okay, so your graph is going to be negative slopes, negative, 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 towards 0, 0, positive, more positive, more positive, more positive, more positive, more positive, more positive. All right. So that's how you distinguish graphically and also algebraically between both, actually no, all three of the original, the first derivative, and the second derivative functions.